Good evening and welcome everyone. Let me know if I'm audible, guys. Yes, no, maybe. Guys, am I audible? All right, perfect, perfect. So, welcome everyone to our 5-day data science bootcamp. My name is Dhananjay Kumar, and I'm excited to be your host and guide through this excited journey of learning and discovery. And I hope you are also excited. So, I think today is the first day of bootcamp, and so how many of you are excited for this bootcamp? 5 days of bootcamp. Just comment Coding Ninjas OP in the chat box, guys. Coding Ninjas OP. All right. Coding Ninjas OP, OP, OP. All right. Great. Great going. So now tell me one thing, guys. How many of you remember today's speaker? You can just type in the name of the speaker or yes, no, maybe. You can guess the name of the speaker. I think the people who would have gone through the landing page properly would have seen like the day one will be conducted Sanil Hussain. Right, right, right. Mohit, it's not Hussein, it's Hossein. Sanil spelling means like you did it right. All right. Perfect, Amit. Absolutely correct. Absolutely correct. So yes, we have an amazing great guest speaker today. That is Sanil Hussain, who will be joining us today and who will be leading a live project on data mining and unlocking the power of big data, where he will be sharing his expertise and experience in this field. He will also be helping you to understand how to make a sense of large amount of data and to how to use it for the meaningful projects and all, you can say so. And it seems like Sanul is already here. Let me check. Hey Sanul, can you hear me?
Yes.
All
Hello,
right,
everyone.
perfect, Sanul. So Sanul, like, how are you doing today, right now?
I'm doing great.
All right,
I'm doing
perfect.
great.
So Sanul, like, if you could please give a brief introduction of yourself to every data science and machine learning enthusiast sitting over here and watching you live.
Okay. So I can see a lot of people in the chat. So hello, everyone, and very good evening to all of you. So my name is Sanil Hussain. I'm an incoming software engineer at Goldman Sachs Warsaw. And so today we are going to talk a lot about data mining and also a lot about big data, how everything works, what is the flow of everything, how you should be learning everything. And we will be deep diving into each of these things. So shall I start, Dhananjay, or are you going to tell?
I think one thing I need to deliver to the students that I encourage everyone here to be open-minded and take advantage of all this opportunity to learn and grow together with Sanil Hussain. And together we will unlock the power of big data with Sanil Hussain, right? So let's get started and make the most of these 5 days. Sanil, the stage is all yours, and
Okay.
we can.
So thank you, and let me just. So we are going to do a lot of things. So let me just structure it once. I will present my screen. So window, home tab. Just let me know once if you can see the screen, guys. So I feel there's a lot of delay in the YouTube streaming, but no worries. If you can see the screen, do let me know once, okay? If you can see the screen, do let me know once. I guess we are doing great. Okay, fine. So let me just start. So you can have so much of data that you don't even know where to begin. and you don't know how to sort through it to get useful insights, right? So which is the whole point of getting data in the first place. And this is where we turn to data mining. Today, you will see how you can quickly use both simple and sophisticated methods to get a better understanding of how to mine data for value and in turn reach the goals that are important to you. And with that, let's get started. So, while the session is designed as an accessible introduction to the field of data mining, it works best if there are a few things you already know. So that's a prerequisite which you need to have, which you need to keep in mind. The first thing is you should already know, and you should already be familiar with Python programming language and the Jupyter notebooks and Anaconda environment. And if you have previously worked with Google Collab, that's a very plus point, because today we are going to use both Google Collab and Jupyter notebook in case that's useful. So it's helpful if you're familiar with the basic statistical concepts. So type in the chat one if you have used Jupyter notebook or Google Colab previously, and if you are familiar with the Python programming language. Just let me know once in the chat by typing one. Okay. So fine. Okay, that's great to know. So now, so if you are going to go out on mining, then you need the right tools. So when you are mining for data gold, that means software, and the two most common tools for that are Python and R. So there are a few good reasons for choosing these two languages. So Python is currently the most popular language for data science and machine learning. It has an advantage of being a general purpose programming language, which means millions of people know how to use it because it can program basically anything. It's also well adapted for data, and Python also is really easy to learn, as you all might know, and it has a very clean, readable syntax. Now, talking about R, R is a different kind of language. I know that it's a programming language that's specifically developed for data analysis. Okay, so consequently, it's very popular with scientists and researchers. So it's what I learned first as a way of working with data. Either one works great for mining data, but I do want you to be aware of some other options as well. So these are not the only two options, there are other options as well. So I want to make sure to mention applications with point and click GUIs, or what you call graphical user interfaces, that are developed with data work in mind. So some of these are free, some are expensive, some are similar to spreadsheets, some have extensive programming abilities. Okay, so they include apps like SPSS, very popular for analyzing data in the social sciences, which is where it was first developed, or what you call SAS, which also has strong programming abilities. Jamovi is also a free open source application that resembles SPSS but runs on R and is one of my personal favorites. So you can see another one is JAS, which is also a free open source application that strongly resembles SPSS and Jamovi. And then there's also Tableau, which is specifically for data visualization, but it's one of the go tools for people who are trying to get a feel for large data sets. Okay. So now, in addition to these apps, one language that anybody who's going to work with data should learn is SQL, okay, what you call SQL. And it's called structured query language, if you're familiar with that. So who have worked with SQL before? Please let me know in the chat with a one. Okay, that's great. So okay, fine, perfectly fine. So, and it's like, this is for accessing databases, and especially if you are working in large organizational setting, you're going to have a lot of data in databases. So, SQL has a great learning return on investment. It doesn't take much to get most of the things that you are going to need in SQL and get ready accessing and cleaning and querying data. Okay. So I also want to mention the spreadsheets. You already know spreadsheets, right? So the rows and columns of Microsoft Excel and Google Sheets. The reason these are important is they are single most common data tools in the world, and that's my personal belief. Other might have different beliefs, obviously. So everybody has them, and a good chance is if you're working with a client, they may provide you with data in spreadsheets. They may want the results back. Okay, so they are great for browsing data, they are great for making very simple graphs, and anybody who is going to work with data owes it to themselves to be very comfortable with both of these spreadsheets. Okay, so now I want to give you my personal philosophy about data tools. I see an order to things. So generally, I recommend that people start with the simplest tools, and that would be spreadsheets, until the data you are working with or the analysis you need to do become unwieldy. Okay. So then consider the next step up. That's an application like Jamovi or SPSS. These allow you to do a lot of specialized procedures for analyzing and mining data, or use a data mining specific application like Rapid Miner or KNIME. Okay, so you call it KNIME. If you know that, you know that. So, but only then should you consider taking the final step to programming languages. And they are, of course, the most flexible and powerful, but often they are also the most difficult to learn and to use proficiently. Okay. So now I do want to give you a little bit of data about programming languages and apps for context. So KD Nuggets is one of the most common and popular sites for information about data mining. So KD here stands for knowledge discovery, and this is their most recent survey of software use among practicing data miners. Okay, and what you will see here is that Python is number one in the list, where 66% of the respondents said that they use Python on a regular basis. Okay, so 51% said that they use software application called Rapid Miner, and it's popular, but the survey people say that they may have been because the survey was actively promoted on a Rapid Miner discussion list. So Rapid Miner has 51% results, and R is third at 47%. And please note that the Excel and the spreadsheet is here at 35%. Anaconda is really a distribution of Python, and then there's the language SQL here at the end. So it lets you know some of the things that are frequently used in data mining. Okay, now I want to give you another perspective on this is postings for data science jobs on the job site Indeed. And this is from 2017. It's a little old, but the pattern is consistent over the time. So even now data science jobs are a boom. So what you see again is Python here is at the top. SQL is close behind. It is still an important thing in data science. Then if you come down here, you'll see that R is still in demand. Okay, any of these can be very useful tools for data mining. So do let me know once which of the languages you see right now on the screen you are familiar with. Do let me know once in the chat. Okay, people are familiar with Python, Java, SQL. Okay, okay, all four, all four. Nice, 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 nice. Okay, okay, got it, got it, got it. Okay, so consequently, I want you to choose your tools wisely. You have a great flexibility and choices. I'm going to be emphasizing more on Python and R in the session, but you have a lot of other options. Okay, so almost any tool you can choose can do almost any analysis if you give it enough work, but do some things. Okay, so look at the client's requirements. So do they use a particular software, application, or language that they want to use? Obviously you would want to work with that, and Python and R are common. Okay, but use what works best for you and the particular project you are working on. Okay, and that can get you started on getting some insights from your data as you mine through it for the valuable insights. Okay, so now I know the session focuses substantially on how to program analysis to mine data, but it is also important to think about the context in which that programming takes place. Okay, that is project as a whole. And when it comes to data mining, there is in fact a well established framework for projects. Okay, so the framework is called CRISP-DM, and that stands for cross industry standard process for data mining. Okay, it's called CRISP-DM, cross industry standard process for data mining. It describes 6 phases to data mining, and I will give you a quick overview of each of these. Okay, so now if you see, the first phase is business understanding. So this is where you do things like determine the business objectives, the thing you are trying to accomplish, the situation assessment, and then determine data mining goals and produce the project plan. Okay, the second phase is data understanding. So this is where you collect the initial data, you describe the data, explore the data, and verify the data quality. Okay, so you have to collect the initial data, then you have to describe the data, then you explore the data efficiently, and then you are verifying that if the quality of data is good or not. And finally, after that, there is third phase, which is called data preparation. Okay, this includes describing the data set, selecting the data, including the rationale for including or excluding particular cases. Then you have cleaning the data, constructing the data, which means things like derived attributes and generated records, and then integrate the data, so merging it with other sources, and then formatting the data to make it so it fits with the existing data, and so it fits the software that you are going to be using. Okay, then you have the fourth phase in CRISP-DM, which is called modeling. This is where you select the modeling technique and check the assumptions, generate the test design, build the model, including looking at the parameter settings, the model description. Then you can assess the model. That's looking at things like how well does it fit into the data. Okay, and do you need to revise any of the parameters that you used? So after this, you have the fifth phase, which is called evaluation. So this is where you can evaluate the results. So you can see how well the results work with regards to the business success criteria. And then you can review the process, determine the next steps. That's a list of possible actions or perhaps the final decision. Okay. And then you have the sixth and the final phase of CRISP-DM, which is deployment, where you apply the conclusions to the problem to be solved and the reason you designed the project in the first place. So this includes planned deployment and plan monitoring and maintenance, see how well it holds out, producing the final report or presentation, and reviewing the project, including the documentation of the entire process, so it can be evaluated and possibly replicated in the future. So that is CRISP-DM, one of the most common process description for data mining. So do let me know in the comments if you have any questions till now. Yes. We will share the PPT of this presentation. No worries. Venkat, it's both theoretical and practical. Okay, it's both theoretical and practical. So you have to know theory. Okay, you have to know theory. Without theory, you can't write code, right? So yeah, let's move on to the next part. So I know we are here for some technical training, but I want to take a minute and remind you that data mining, like basically everything else, takes place in human social context. It is important to respect the people who provided the data or who will benefit from your work. And there are a few important dimensions to that respect. Okay. The first important issue in data mining is privacy, which affects how you gather the data, how you store the data, and what you share. So this is both an issue of good manners, and as it happens, there are several major laws. Okay, so let's talk about the other continents. So, for instance, in the European Union, there's the GDPR, that's the General Data Protection Regulation. If you see in California, there is the California Consumer Privacy Act, or CCPA. In the US, there's also the federal level HIPAA, the Health Insurance Portability and Accountability Act, which is going to affect the health records. Okay, and then there's FERPA. Okay, this is the US Family Educational Rights and Privacy Act. So if you're working with any educational data, this is another important set of regulations you are going to have to work with. And all of these are regulations that have tip. They are very specific about some of the things that you can use, what you can't use, or how you have to process the data to meet privacy regulations. And there's a lot more details on each of this. But if you're working with data from the European Union or in California or health records or education, anything, you owe it to yourself to take a little bit of time to see how each of these regulations deal with privacy. So privacy is very, very important. Okay. Now, there's also copyright. And this is important because data mining often uses data that's found on the web. And you know how you can't, for instance, just use any pictures or video you find online because they may still belong to the people who created them. So there are a lot of things like you see NCS, no copyright strike. So why people use those things? They could have easily used any footage from any music. So you need to have the proper license. Now it may be that they put a Creative Commons license on there and make it so nobody can use it, but it may be restricted and proprietary, in which case you need permission or possibly to pay a fees. Okay, so you have to pay that fees to use that thing in your own content. The same thing is true of data. You can't assume that data can be freely used just because it's present on the web. Just because you see the numbers in front of you doesn't mean you can take them. Okay, that data belongs to somebody, they put it there, and you have to check the license to make sure that what you are doing is permissible. Okay, so I hope you got the point. Okay, so now there's the issue of whether your data is potentially biased or not. If you check a lot of elections which happened in the US, you will see there are a lot of fake news which are biased towards a particular person. So you have to check if the data is potentially biased or not. And I think of a few elements in this. Number one, anybody who's worked in computer programming knows GIGO, which is basically garbage in and garbage out. So do you know, like, have you heard of this term before, GIGO? Have you heard of this term before, GIGO, garbage in, garbage out? Okay. Okay, no worries. No worries. Okay. So, like, what that means is if you have bad data well, you may have a great algorithm. Okay, no doubt on that. You may have a great algorithm, but if you start with a bad data, you are going to end up with bad conclusions. So even if you have very sophisticated approaches, very sophisticated algorithm, if you start with a bad data, you are going to end up with bad conclusions. So you need to check the quality of your data before going in. And that includes representativeness. Specifically, do you have a sufficient diverse data set, that the data set that you train your model on matches the data that will be coming in once you put your model out there on the world. So you have to have diverse data sets. You can't be biased on a particular data set, because when you will have new data, when your model will be put forward to new data sets, then it might give a bad result. So you need to have diverse data sets so that your model can train on these diverse data sets and can be prepared for any new data set. Okay. So you want to look at the diversity, the spread, both of people and of situations, and the weighting, how much emphasis you put on each kind of case in your training sets so it can transfer well to the testing data. And then there's an issue of construct validity. That really means, are you measuring what you think you are measuring? And it has to do with interpretation, because there's often a gap, or at least a slight mismatch between what you want and what you have, specifically in data mining, because you're frequently using what's already there. And so it's very important to interpret things in the most precise manner that reflects what it actually meant when the data was gathered. Okay. So now I know mining is very hard. If things you wanted were sitting right there on the top of the ground, just like watermelons, you won't have to dig up so much dirt to get the valuable things that are hidden. The same thing is true in data mining, except now, instead of looking for copper, we are looking to find that signal that's hidden in the noise of data. Okay. So we are trying to find the meaningful and actionable patterns in the randomness. But there are a few things you need to be aware of. And one of the most important is that with enough parameters, with a sufficiently complicated model, your model can fit any dataset perfectly. But that doesn't mean it's going to work well in practice. This is known as the danger of overfitting, in getting a model that is much too specific to that data that you currently have. Okay. So the problem is that when a model is too closely meshed with the data, it doesn't work well with the new data. This issue can go by several names. You can call it statistical model validation. You build a model on your sample data or your training data, but is it valid? Does it work well with the testing data or with the new data? In some circumstances, it's called external validity. Okay. So how well does your model work when you go out the door from your lab to the real world? And then there's the catch, all term of generalizability. How well does your model, the thing that you did all this work and data mining for, how well does that work with the new people? Okay, the enormous variety that you can encounter, for example, when you launch a new social platform. So now these are important issues. Fortunately, there are several ways to assess the validity of your model, to try to estimate how well it's going to work when you go beyond the data that you build the model on. Okay. So the standard method from the laboratory sciences, like the one I'm trained in, is usually done manually and in great detail. It says, check the data. So you are actually going to do a hands-on verification of the distributions, whether you have outliers, whether you have anomalies. Then you might check the fit. How well does your data match the assumptions of your statistical procedures? How well do the data fit the particular model? Then you can check the sample. Okay. So you are going to look at it more closely. Does it appear to be representative of the overall population? Are there unusual cases of missingness in the data? And then when you are all done with that, just like you just like do the study, get more data, do it again. Okay. Just a second. Just a second. Okay. So After that, we have, so now you can think about validation happening at 2 points in time. So the standard model that I just described assumes that validation happens in the future. So you do the study again with a new sample. This is a replication, and maybe you will do it in a different place or maybe with a slightly different method. And when you are done, you can combine the results or at least compare them to see how consistent they are over time. Okay. So on the other hand, you might want to do things right now. With enough data, you can do replications with what you currently have. And there are a few general ways that this is done. One is referred to as holdout validations, and the other is referred to as cross validation. I will describe each one of these. Okay. So with the holdout validation, you might want to do things right now. Okay, so what you do is you split the data set into two parts. One is called the training data set. That might be 70% of the data. Sometimes it is 80%, sometimes it is 90. And the other part is the testing data set. Now that's the rest of the data. And the idea here is you train the model, you build your model, you do all your mining on the first part, the training data set. And then once you have come up with a really good model that you are confident in, you test that model on the second part. Now, the idea is you only touch the second part once. You do all of your work, all of your evaluations on the training data set. And sometimes you can have a third part that goes in between called a validation data set, which lets you compare several different methods that you are exploring and evaluate them on another data set and then pick the best one and apply it to the testing data set. Now, I will use this method in many of the demonstrations in the session, so don't worry about that. So I also want you to be aware of cross validation, and this is where you split your data set into k folds or segments. So k is a number that you choose, and it might be, for instance, 3, 5, 10, 20, anything. Okay, and the idea here is that you take all of the parts except one. Okay, you take k minus 1 parts and you train the model on those, and then you test the model on the remaining fold, and then you rotate through the data set k times, so each fold can serve as a test set. I hope you got the point. Okay, so you can take 3, 5, 10, 20, anything, and except one part, you take k minus 1 part, you train the model on those, and then you test the model on the remaining, and then you rotate the data set k times, so each fold can serve as a test set. So that's what it is. Now you can think of it this way: cross-validate many models on 60% of your data, or maybe it's 50%, or maybe it's 80, some percentage, and then you validate the model on 20%. But you rotate through and you try it again each time, and then you find a good model, the best one, and you taste that on the last 20%. And I will demonstrate this approach with a few of the procedures that we have in this session. Okay, so the idea here is that all of your work in data mining, that's the digging, the sorting, and the sifting through the data and models, allows you to find the greatest value. And then these validation methods allow you to verify your findings and proceed to the implementation with confidence. Okay, so that's the end of the first part. Now I have a few questions for you, which you need to answer me in the chat. Okay, which you need to answer me in the chat. So the first question is, if you're working with educational data, which privacy regulations are you most concerned with? You have the option. The first one is FERPA, second one is HIPAA, third one is GDPR, and fourth one is CCPA. So we talked about this earlier in the regulations, in the privacy part. So tell me. Yes, yes, yes. Yes, it's FERPA, it's FERPA. So people who are actually interested in the class are actually paying attention. So glad to hear that. Thank you. Thank you. Thank you. It's FERPA. Yes. So the second question, where is your data mining conducted using holdout validation to do replications? So the first option is in the testing data set. Second is in the nested data set. Third is in the training data set. And fourth is basically the training and testing data set. Which one? Three or two? Which one? Or one? Which one? Four? It's in the training data set. So people who answered three are right. Let's move to the third question. So basically, in which phase of data mining does Crisp DM have you collect initial data? So option one is the data preparation phase. Option two is the business understanding phase. Option three is the data understanding phase. And option four is the modeling phase. Tell me. Which one? Modeling phase. Data understanding. Someone answered data understanding. Who is it? Furkan Ali Khan. Well, Furkan, you are right. It's the data understanding phase. Vijay Kushwaha, yes, three. It's right. Data understanding phase. So it's the data understanding phase. Okay. Now, before we proceed to the next part, so I want you to show something. There is a recent data set which I got for layoffs. Okay, just let me share this tab. So can you see the tab? Can you see the new tab? Can you see the new tab? Just let me know in the chat if you can see the new tab. Okay. So if you see clearly, in the recent layoffs, like I was really like shocked at the number of layoffs that happened in the previous few months. Google laid off, Amazon laid off, Microsoft laid off, Meta laid off, Goldman Sachs laid off, and many other companies laid off. So I did some analysis and saw that if you see clearly, Amazon laid off 18,000, Twitter laid off 3,700, Google laid off 12,000, Spotify laid off 600. Spotify is quite well known for data science jobs, data engineering jobs. So Spotify is a lot focused on that thing. So if you see clearly, you can see total 6% of Google's workforce got laid off. Total 13% of Meta's workforce got laid off. 5% from Amazon, 50% from Twitter, 6% from Spotify, 13% from Uber. So after all these layoffs, the percentage of data science jobs, okay, the percentage of data science positions which got laid off in the company, for Amazon, it's 1 to 2%. Like 1 to 2% of the workforce who worked in data science in Amazon got laid off. But in the SD field, in the SD role, 50% of the job positions got laid off. So if you look at 1,800 layoffs, only 1 to 2% people who worked in the data science position got laid off, but 50% people who worked in the SD position got laid off. If you see Twitter closely, 3,700 total layoffs. Out of that, 8.3% were data science and ML positions, and 25% were SD positions. If you see Spotify, 600 got laid off, but out of that, only 1%, like 6 people only got laid off who were in the data science role. But 11.17% got laid off in the SD role. So you can clearly see how much important is data science job right now. And it's not only for right now, it has been there for last 2, 3 or 4 years. Even if you consider 2017, you will see data science jobs were very, very important. And definitely if you are learning data science currently, in the coming decade, in the coming 5 to 10 years, you don't have to, have that insecurity. Will I have the job? Will I be laid off by some companies? you can clearly see the SD percentage is 50%, but data science percentage is 1 to 2%. That's a huge difference. And moreover, if you look at the salary range of a data scientist in India and SD at India, if you consider Amazon, then the salary range of data scientist in Amazon is much more than SD at Amazon. So for an SD, the salary range can go up to 64 lakhs, but for a data scientist, it can go as up as 75 to 80 lakh per annum. Okay, so that's huge. So you should be considering to learn data science right now, because it's going to be in the boom phase in the coming decade. And you can obviously learn it from any sources. And currently, you can see we are having a session at Coding Ninja. So Coding Ninjas also has this data science course, so you can go and check that out as well. Okay, so moving on to the next phase. So I will share this tab right now. So we have done the questions. So I'll be sharing this tab right now. Okay. So one more thing which I wanted to share was, okay, I will share that later on when we will be coding. I will share you the exercise files through Google Drive. You can just use those files in your own laptop or PC, and you can run the codes. Okay. So starting off with, so data mining comes into its own when you are dealing with lots of data, and you may be familiar with the 3 V's that define big data: volume, velocity, and variety of the data. So it turns out paradoxically, you can have too much of a good thing. Having lots of cases or observations is generally good, but things get much more complicated when you have many dimensions or fields or features or variables. And there's few reasons why that can be a special challenge. Okay, so some of the problems that come up with high dimensionality include an exponentially increasing complexity and demands. So you have so many more possibilities, and it becomes so much harder to compute it. That's because each dimension is an additive, it's multiplicative. Also, with each variable, you have idiosyncratic error. That means each variable doesn't perfectly represent the thing that you are hoping that it measures. Okay, it represents something close to it, but it brings in its own little bit of noise. And when you have lots of different noise, it becomes harder to find the signal in the data. And ultimately, you have to find that signal from the noise, right? Now, you have the risk of overfitting, which we discussed earlier. If you have 1,000 variables in there and just at random, 17 of them are super correlated with your outcome. Okay, 17 of them are super correlated with your outcome. Your algorithm is going to latch onto those. But if you have those 17 variables and if they are affected by the noise, it's not going to generalize well when you go to another situation. And finally, when you have a lot of variables or dimensions, you have issues with interpretability. If you're building a model that a human has to understand and it's got 700 variables that interact in very complex ways, it's nearly impossible to make heads or tails if it's for a human driven decision making. And so there are some solutions to these particular problems. One is to combine variables to reduce the complexity or dimensionality of your dataset. One interesting thing about this is, in general, the errors associated with each variables tend to cancel out when those variables are combined. Okay, so these gives you more stable measurement, and it gives you better generalization of the model which you are using from the current data to a new data. Okay, also because now you have a smaller number of dimensions that you are dealing with, it may be easier to interpret the model and have a human decision maker apply in their process. Okay, now the general concept with which we are dealing with here is dimensionality reduction, or fewer dimensions. So if you attended my previous boot camps conducted by Coding Ninjas, we dealt a lot with dimensionality reduction. we had 2 bootcamps earlier. Every time we dealt with dimensionality reduction. And the idea here is to project the data into a lower dimensional space while preserving as much as the useful variability and interrelationships as possible. Okay. So there are a couple of metaphors for this. One is to think of a hand's shadow. A hand is a three-dimensional object, but a shadow is two-dimensional, right? Now, depending on the position of the hand, the light source and the surface, you can get a shadow that, might be a little bit ambiguous, but like we have here on the left, but the shadow on the right is readily identifiable as hand, even though you have lost one of the dimensions in the process. So you can only see the shadow here, right? You can't see the hand here. So you are reducing the dimension, but also preserving the feature. So that's dimensionality reduction. Now, a similar process can happen with the data, and you can get the data shadow as a way of thinking about it. For example, a scatter plot like this show is a two-dimensional representation, right? So we have got our x variable across the bottom of our variable y, and each dot represents a pair of values for each cases. Okay, so you can see all these dots. So we have 2 dimensions, x and y. Now you can see here on the vertical dimension, we have got a fair amount of variability. It goes from -4 to +4, right? Now we have the same thing on the horizontal. It goes from -4 to +4 again. And so we have 2 distinct dimensions. Okay. Now, if we were to rotate the plot, so it goes on the regression line that's in the middle. Okay. Then we have almost no vertical variability, and we have enhanced variability on the horizontal axis. And at this point, instead of talking about 2 dimensions, we can talk about a single common component or dimension, and it makes it much easier to deal with the data. Okay. Now, there are many choices, many algorithms for dimensionality reduction, but there are 3 which I want to show you in this session. So the first one is PCA, okay, which stands for Principal Component Analysis. So have you heard of this term PCA before? Let me know in the chat once. Yes. Okay. Okay. No worries. No worries. Okay. So it's far and wide the most common method, and along with the closely related factor analysis. And what PCA does is it looks for components. Those are like combined 2 dimensions that can account for several factors or variables at once. The same way we rotated the scatter plot before, right? So we saw one clear dimension there that we could use instead of 2. That actually shows you that the rotation is an important part of the interpretation and implementation of PCA. Okay. Now, another method is LDA. So it stands for linear discriminant analysis. And again, my question to you, do you know about LDA? Do you know about LDA? Okay. Okay. No worries. No worries. Okay. So it's called linear discriminant analysis. And what this does is it's designed to separate cases or, your observations into different classes or categories. So it's actually a method of classification, but it uses these underlying concepts to do it. So it combines the variables in the data set into dimensions that can separate the classes cleanly. Okay. So now there is one more sophisticated method, which is called TSNE. Okay, TSNE. So again, my question to you: do you know about TSNE, or you are hearing it for the first time? Okay, just give me a moment. I need to drink water. I'm feeling a bit thirsty. Just give me a moment. Just give me a moment. Okay. So where were we? Okay. Okay. Completion of this course never heard before. Can you just say? Okay. So okay, no worries. So TSNE, it stands for T distributed stochastic neighbor embedding. Uh, it's a long name. No worries. You can just go and search it up on the internet. So it's called T distributed stochastic neighbor embedding. This is an example of a non-linear dimensionality reduction, and it's good for showing probabilities of pairs being connected in points. And if you have the data that's arranging the helix like this one here, or you have circles or ones enclosed in the other, than TSNE can be a very powerful method for finding the dimensions. So even when you can't draw a straight line between things, it can be very powerful. Any of these methods, PCA, LDA, TSNE, and many other things, that can be ways to help you sort through a large number of dimensions or variables in your dataset and combine them into smaller, more stable, and more generalizable factors, or what you call components, that can help you more easily find the value in your data. Okay. So ultimately, we have to find the value in our data, right? Now, I will be like enough of the theoretical classes. Now we will be coming into the practicals. So the first thing which we will do is I have a exercise file. Okay, I have exercise file. So how to share it? How to share it? I have to check once. Just a second. Just a second. Let me uh, let me just share it in the Google Drive, and then I can share the link with all of you. Dhananjay, if you are in the live session, can you tell me if that's possible? Like, can we share a Google Drive link so that the students can download it? Just a second. Okay, so just a second. I think I can share it as well. Chat with. No, I can't share it. Okay, I am sharing to Dhananjay. If he's in the chat, he will be sharing it with you. Okay. Fine. So let's start. Or Dhananjay, what we can do is uh, after we finish off with the code, then we can share so that we can develop the flow and people don't misinterpret the things. So after we finish with one file, we can share the file. So that works better, I guess. Okay, let's start. So okay, so first of all, I will be sharing this tab. I hope you guys can see the Google Collab tab. So if you don't know what Google Collab is, you can just come up here, Google Collab. Just search Google Collab in the in your tab, and you will see the first option. So Google Collab, COLAB, it's COLAB. So just click on the first link. Just click on the first link, and then you can just write your name in the new notebook. Click on new notebook, and you can just give some name to your new notebook. And what you will do is, let's give it name, Coding Ninjas Big Data Workshop. Okay, so first what we will do is, I have a file which I will be bringing here. So let it connect once. Just a second. I guess it's connected. So now, okay. So I have the sample data file here. So whenever you will open Google Colab for the first time, you will have a sample data file here. So I will be pasting a file here, or maybe I don't need to paste something here. We can just write it customly. So just make sure the things are doing great. Okay, what we can do here is, okay, I need the data opt digit CSV. Just a second. So I need to push a file up here, else our program will not work. Okay, got it. Okay, fine. So the first thing is, there is one data set here. So there is one data set here. So if you can see clearly, there is this data set here, and this is called opt digits raw CSV. So you'll be using this data set Okay, we'll be using this data set. So let me just close it. Okay, so first of all, what we will do is we'll import some libraries. Okay, so first of all, we'll import some libraries, and I will make you understand each of the things, so don't worry about it. Already you have got the code file, so you can follow along with that, and let me explain the things. Okay, so you can follow along with that code as well. So let me show you how all the things work in Python. So to do this, I am first going to load some libraries and functions, and then I'm going to load the data set. So the libraries which I need are, so first of all, I need to import pandas. Okay, I need to import pandas as PD. Then why it's happening? Okay, then I need numpy as well. Okay, so you can write any name here. I generally use NP, and others also use it as NP only. Then we have matplotlib. Matplotlib. Okay, done. And finally we have cbond. Just follow along and don't worry, I will explain everything. Don't worry about that. So from sklearn model selection, import train test split. Let's run it once. Okay, fine. Then we have the next code. So we will now load the data set with the data set which I showed you there, OPT digits raw CSV. We will load these data set. So for that, we need to write df equals to pd dot read. So since we have the data under the sample data folder, we have to first write sample data. Then we have to write opt digits raw.csv. Let's import this. What happened? What happened? Just a second. Just a second. Acha. Okay. So after this, so now I have loaded the data set. Now I have saved this as a local CSV file to make it much easier to deal with, and it's in the sample data folder for this session. So I'm going to open this data file. Now you can read it directly from the I will just open this once more. So you can read this data from the University of California Irvine Machine Learning repository. So if you want, just uncomment the 3 lines. So you might have the code file, right? So there is 3 lines, which is this one. There is these 3 lines. So you can uncomment these lines and go and check that repository. You will find these data set there. Okay. So after this, let's take a look at the data very quickly. So we have 5 rows here. Okay. So if you see clearly, let me just go here. I will just come up with df.head. So you will see there are 5 rows here. Just a second. So there are 5 rows here. Okay. So just a second. Okay. So you have 0 to 4. Okay. So these are the 5 rows. And then we have the numbered columns. So you can see the numbered columns, right? We have 0 to 64 columns. So these are the pixel data. And then the very last one is the class identifier. Okay. So these are the pixel data, and the very last one is a class identifier. Now what we can do is, so okay, after this we have to rename the column once. So let me just paste this data here. So we have to rename the columns now. So these are so that they are a bit less informative. So I will just run this code once more. Where did it go? Okay. So we have to write here df.columns equals to p plus str I for I in range 0 to length of the column -1. Just a second. And after that, we have to write. Okay, so we have to rename. So we have renamed all the columns so that they are a little more informative. Now, what I'm going to do is I'm going to take the attributes. Okay, so the ones that tell us how many pixels there are in a particular part of the image, and I'm going to rename them starting with the P for pixels. Okay, so what we have to do is I will just make another code here. So df equals to df dot lock df dot y dot icing. We have 1, 3, 6. Okay. After this, I will just see the 5 rows once more. Okay, now got it. Then we have to split the data, and I will just get to this part once. Okay, so now we will split the data. So I will write one more code file. So what we have here is we will rename the columns right now. So as I told, we have to make them less more informative. So what I'm going to do is I will take the attributes, the ones that tells us how many pixels there are in a particular part of the image, and I'm going to rename them starting with the the P for the pixels. Okay. So what I will do is xtrn x test y training y test equals to train test split. What I will do is df.filter regression expression rejects. After that, I have to df.y. Then I will keep the test size as 0.30, and finally random state equals to 1. Okay. Now we have renamed the columns, right? So okay, so then the last one, lowercase y, which is what I just call a class or outcome variable. So I run this command once. Let me just run this command once. Okay, where did we go wrong this time? Okay. Again. df.y test size equals to 30, random state equals to 1. Let me just create the training data sets once. So trn equals to x trn y equals to y trn, and finally the testing data set. Okay, bracket. Okay. After this, we have to make the testing data set tst equals to x tst. Then we have to make the y test y tst. Let's run it now. Okay. So as I told, a lowercase y, which is what I just call a class or the outcome variables. So unless I have a reason to use something else, I will use that. So I have run this command, and then also the data set includes the numbers 0 through 9. Okay. So I will just explore the training data set once more. I will display the images after this. You will see the other data set has numbers which includes 1 through 9, like 0 through 9, and that makes sense. But to make our demonstration work a little bit faster, I'm going to restrict it to just numbers 1, 3, and 6. So what I did here is I restricted the numbers to 1, 3, 6, so that our demonstration works a little bit faster. But you can keep it anything. So this command will restrict it to those numbers only. And okay, one more thing is, when we look at the first few rows, so you can see we have rows 4, 11, 14, because these are the ones that have the 6, the 1, or the 3 in them. Okay, these are the ones that have the 6 or the 1s or the 3 in them only. And so this is the data set that we are going to be working with. There is, however, one additional step we need to take, and that's because we are using machine learning algorithms, and it's most common in the situations to do a training and testing data set. So that's the reason I wrote this lines. So we have to have a training and the testing data set. So we have a large data set, so we can make it split. I will be using the training test split function, which I used it here. Okay, and creating the X training and Y training and X test and Y dataset. Okay, so this is why I split up the way that we need to, and now we can begin exploring the training dataset. So just I will write the next few lines of code here. So I'll set up a grid for the image. X equals to plt.subplots, and rows equals to 1, and columns equals to 20. And then we have the figure size 15, 3.5. I will tell you why I used this. After this, we have just a second. I'm not able to run, getting some errors due to data not found. Acha. You don't have the data set. You don't. I didn't share the opt digits.raw CSV. So that's the reason. That's why you can't write the. You can't read the data. Okay. Just a second. Okay, if you are having a problem with the first few codes, I will just explain once more. No worries if you are not getting it. So the first thing we did here was we imported some of the libraries so that we can work with the rest of the data, and then we imported the CSV file on which we are going to work right now. I showed you the first 5 rows from the entire data set, and after that, so you can directly read it from the this data set which I showed. You can directly read it from the repository, which you can see in the coding file which I shared few moments back. So if you look at the data set very quickly, you have 5 rows that starts from 0 to 4, and then we have few numbered columns. So these are the pixel data set here, and the very last one is the class identifier. Just a second. The very last one is the class identifier. Now I renamed these columns so they are a little more informative. And what I'm going to do is I am going to take the attributes, the ones that tell us how many pixels there are in the particular part of the image, and I'm going to rename them. Okay, so this is where I did the thing. I picked up the attributes and I renamed them. So now the last one, a lowercase y, which is what I just call, starting with P for pixels. So I run this command, and then also the dataset includes the numbers 0 through 9. Okay, if you see clearly, the dataset includes the numbers 0 through 9, and I have a reason to use something else. So now to make our demonstration work a little faster, I'm going to restrict it to the numbers 1, 3, and 6. You can see clearly here, I restricted the numbers to 1, 3, and 6, but you can take anything if you have time. Okay, so this command will restrict it to those numbers only, and we'll take a look at the first 5 rows. So df.head, it gives us the first 5 rows. Okay, you can see here we have rows 4, 11, and 14. because these three are the ones that have the 6, the 1 and the 3 in them. Okay, the 6, the 1 and the 3, we restricted it to these numbers only. So you will see only those rows which have 3, 6 and 1 in it. Okay, so 4, 11, 14, these are the rows, and 24, 27, these are the rows that have 1, 3 and 6 in it. Okay, I hope you got okay, just a second. If you are having problem with not running the data, I will share the data set also as well. So just a second, just a second. You are having problem with not getting the data. Just a second. I will share the data set as well. I will share the data set as well. Okay, I have shared it with Dhananjay and he will share it in the chat. No, you don't have to create a folder named data. You can use a sample data folder as well. Okay, there's no issue with that. You can use a sample data folder as well. And instead of writing the when you are reading the file, when you are reading this file, so I will show you once. When you are reading pd.read CSV, instead of writing data here, you can write sample data here, just as I wrote. Okay, and you have to push that OPT digits raw CSV file inside the sample data folder. Okay, then you can use it. You won't get an error then. Okay, you won't get an error then. Okay, let me just finish with this part. Okay, now we will be exploring the training data. Okay, so what I did was I split the data sets into training data and testing data. So I created X train, X test, as well as Y train and Y test. Okay, and now what I will do is I will just explore the training data. So for that I have to, okay, just a second. So we have subplot KW equals to dict S equals Y equals fine. Just run it once. Just a second. Again, a problem. Okay. So we have to. I will tell you what I'm doing. Just a second. So 0 to -1, I guess 0 to -1. Then I will have to reshape it to eight dimensions. And then finally, okay, finally I have to plot it. And then just show the plot. Okay, again an error. Okay. Okay, so if you, why am I not getting the images? Why am I not getting the images? I was supposed to get a few numbers here. Anyways, okay. Anyways, so basically, you can see this is probably a one and a 6. I can't see the numbers here. I don't know why. It didn't show me the numbers here. So I was supposed to get 20 images here. Okay. You can see the grid. I was supposed to get 20 images here that are in the training data set. So this will set up a grid for the images that we will actually plot before, like underlying pixels. So this is basically creating this grid, okay, of 20 images. We were supposed to have some numbers here, but I can't see those numbers here. I don't know why. So you will see if you are getting this clearly, if you are running it on your PC, if you are getting the numbers, you might see some low resolution images, right? And it's specifically a challenge for the algorithm to classify those images and classify those numbers. So although it's pretty easy to tell that there is a 3 or 6 in that number or a 0 in that number, but the resolution is pretty less, so it's hard for the algorithm to classify them. So which is 3, which is 6. If you are getting the clear images, do let me know once in the chat. If you're getting the clear images, do let me know once in the chat. You did not get the file. Acha, you are getting. Acha. Okay. I don't know why I'm not getting. I'm not sure about that. Anyways, so So now what we will do is we will choose a few variables. So let's say we are choosing here P25, P30, P45 and P60. And we are going to take a look at those and their association between them by creating a grid. Okay, so let me write that code here. So what we'll do is we are going to sort, like just sort of at random or haphazard, choose a few variables. Okay, we will just randomly choose few variables. So here we will choose P25, P30, P45 and P60, and we are going to take a look at those and their association between them by creating a grid. So let me write that code here. So G equals to SNS dot pair grid. So training variables equals to, first we will have P25, then we have P30, then we have P45, then we have P60. Fine. Let's keep the hue. If you are not getting white boxes totally clear, that's the same thing that's happening with me. I don't know why. If somebody is not getting the CSV file, Dhananjay shared it. Please see the Dhananjay shared it before. If you check the chat little bit up, you will see the file there. Okay, so you can go and use that file here. Okay, so right now what we will do is, let's create the color palette: red, green and blue. Okay, now we will add the histograms. So Gmap, upper, SNS, KDEP, lot. After that, we will add the scatter plots below the diagonal. So I showed you a scatter plot before, right? So same way, we will add it below the diagonal. Sinus dot scatter plot. And after that, we will use the okay. What happened? Okay, fine. Got it. Okay, so what we have here is, uh, the distributions on the diagonals for the three variables, where one is red, 3 is in green, and 6 is in blue. Okay. So basically, we have the scatter plots, and we have really two-dimensional density plot here. The point here is that you can see that there's separation between these things. Okay, there's separation between these things, and it doesn't even really matter what the variables are, but you can see that there is separation. This is critical for our algorithm to work properly. Okay. And so now that we can check that we have got the data imported, we renamed it, we check that there's going to be an adequate separation, just like this. Just a quick visual check. You can now save the data. So for that, we have to write, just a second. So if you are not getting any warnings here, you might get the correct colors. You will get the correct colors. I'm not getting the correct colors. There's some error with the system. But if you are, if you have everything installed, you will get the correct colors. To let me know, it is showing error. Achha. Sethu, are you using Google Collab? Achha, you are getting, okay, fine. Perfect. So what we will do is, where did it go? Okay, after this, what we will do is we will save the data. So for that, you can directly write df to CSV, sample data. Then we have the OPT digits dot CSV, and we have to write separation, index equals to false. Then we have into CSV. We have sample data, OPT digits, CSV, sep equals index, just a second. Finally, we have to save the test data as well, sample data, OPT digits, test.csv, to use a separator. Index equals false. Let's run this. What happened? Just a second. I think I missed something here. Just I will copy paste and pass something. Okay. Okay, so the data is saved, I guess. So it's still okay. So the data is saved now. So you can save the data now, and if you have already saved the data, you don't need to repeat this. But after this, what we will do is, okay, let's jump on to a next file. Let's jump on to the next file. I will just summarize this entire thing so that you don't get lost here. So first of all, what we did was I imported some libraries. So the libraries we imported here are pandas, numpy, matplotlib, cbond. And after that, we read the CSV file sample data from the sample data folder. So if you are importing, importing the OPT digits, make sure it's placed in your sample data folder, just like here. You see, I placed it OPT digits.tst CSV. I placed it in the sample data folder. Okay, the OPT digits raw CSV. I placed it under the sample data folder. So after that, what we did was we saw the first five columns, first five rows of the data set. Now we have a few numbered columns and the rows are from 0 to 4. So these are the pixel data here, and then the very last one is a class identifier. Okay, so we renamed these columns so they are a little more informative. After that, what we did was we took the attributes. The attributes basically tell us how many pixels there are in a particular part of the image, and we renamed them. So okay, so we started with p for pixels, and the last one a lowercase y, and like I run the command, and then the data set includes numbers 0 through 9, and that makes sense. But to make our demonstration work a little bit faster, I restricted it to 136 only. Okay, so this command will restrict the numbers to 136 only, and we had a look at the first few rows, and here you can see we have rows 4, 11 and 14, and then 24, then 27. You can see only these rows because the 1, 6 and 3 are present in these rows only. And so in this data set that we are going to working with, okay, so there's however one additional step which we did, and that's because we are using machine learning algorithm, and it's most common in the situations to make a training data set and a testing data set. So we splitted the data set into training and testing data set. Okay, so we have a large data set, so we can make that split. After that, what we did was, after the splitting was done, we started exploring the training data set. Okay, so we made a grid to fit 20 images. So unfortunately, I couldn't see the images. But if you are getting the images, it might be in a very low resolution. So you can see either 3, 6, 9, 1 in that image. But since the images are low in resolution, it's very hard for the algorithm to classify them. Okay, so it's pretty hard for the algorithm to classify them, and it's pretty easy for us, but it's pretty hard for the algorithm. Okay, so after that, we randomly chose some variables. So I chose p25, p30, p45, p60, and after this we looked at their association, like the association between them, by creating a grid. Okay, and so we saw there are scatter plots, right? So these are the two-dimensional density plot here. The point here is that you can see that there's separation between these things. So it doesn't even really matter what the variables are. If it's P25, P30, P45, P60 or anything else, it doesn't really matter. But you can see that there is separation, and this is critical for our algorithm to work properly. And after this, we checked that there's going to be adequate separation, just like a quick visual check. So now you can save the data. So which we did here. Okay, you can save the data here. Okay, okay, fine, 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 fine. Okay, so now we will move to the next part. Just give me 2 minutes. Just give me 2 minutes. I will, in the meanwhile, I will share you the next. Okay, just a second. Just give me 2 minutes. Just give me 2 minutes. Okay, so I will be okay. So I have my OPT test and training dataset. I will share it with you once. Again, I have to share this files. Just a second. Just a second. Okay, I'm sharing two files. Keep it under the sample data folder. Okay, I'm sharing two files. Please keep it under the sample data folder. Okay, perfect. Perfect, Situ. Perfect. So I have shared two files. Dhananjay will be sharing it with you. Okay, Dhananjay has shared it. So you can use these two files and keep it in the sample data folder. Okay. So back to the game. Just a second. I have to present it. Okay. So now. Okay. So if you see, we talked about PCA before, right? So by far, it's the most common way to reduce dimensionality in a dataset, and it's what you call principal component analysis. So it's just usually called PCA. So this is a very simple and easy thing to do in Python. So we will first begin by we have already loaded the standard packages, right? So we have loaded the scikit-learn, sklearn. We have loaded the numpy, pandas, and all those things. And we have also so first I will do is what I will do is I will read the OPT digits training dataset, and I will read the test dataset afterwards. So first, let's read the training dataset once. So pd.read CSV sample data OPT digits training.csv. Okay. Okay, done. So what I will do is we will split it. Okay, we will split this data set. So we have the X attribute variables separated from the Y class variables, and then we will do the same thing for the testing data. Okay, so we will split this data into so that we have the X attribute variables separated from the Y class variables, and then we will do the same thing with the testing data. Okay, so what we'll do is X trn equals to trn dot filter regex equals d sin y dot y. Just follow along with me. Okay, just follow along with me. I will explain each and everything, so don't worry. So X training, Y training, we are splitting those two things, and after that we will read the test data set as well. So tst pd read CSV sample data OPT digits test.csv. Okay. So folks who have already modified their training and test data, they can use their own training and test data. And folks who couldn't modify it, you can use the two data sets which I shared. Okay. So you can go with any of those, not an issue. After this, what we'll do is we will separate the attributes, the X and the Y. Okay. So X tst equals to tst dot filter regex equals D, and after that Y tst equals to tst.y. Let's just run it. Okay, so now once we have done that, we can look at the first few rows of the training data. Okay, so for that I have to write training.head. So we will look at the first few rows. Okay, so now you see we have around, just a second. Okay, so we have 64 attribute variables. Okay, 0 to 63. You can see we have 64 attribute variables which are 0 to 63. 0 to 63. Okay, so P is for pixel. The P you see here, it's for pixel, and then the class variable that indicates the what the digit actually is here, Y at the end. Okay, so P is for the pixel, then the class variable is basically the digit that actually is here, and then you have the Y at the end. Okay, so now we have just a second. Okay, so what I can see here is we have 1, 1, 6, and so on. Okay, so we will begin by training the model with the training data. Okay, we will begin by training the model with the training data. So we will set up a PCA object now. Okay, we will set up a PCA object now. So for that, I have to write PCA equals to PCA. Now what I will do is okay, so we are going to project the training data because PCA dimensionality reduction is just like a projection, just like with shadows. You are trying to find a shadow of the data that is still informative about what the original data is. So first, what we will do is we will transform the training data. Okay, we will transform the training data. So trn pf equals to pca.fit transform x training data. After that, what we will do is we will plot the variance. We will plot the variance which is explained by each component. Okay, so plt.plot pca.explained variance ratio. Let's just see. Hope we're not getting an error. Okay, we are getting an error. Just a second. Okay, I forgot to import another library. We have to import another library, which is basically from sklearn.decomposition. Import PCA. I forgot to import PCA. No worries. I have to run each cell once again. Just a second. Just a second. Okay, we are almost there. Okay, now I think this will work. Again, pca.fit transform. What happened exactly? Fit transform string. Fine. Because of this, so just a second. So I set up the PCA object. After that, I'm transforming the training data. So training TF equals to PCA.fit transform. Acha, just depose. Okay, fine. Acha. So what we did here is we set up a PCA object and we are going to project the training data because a PCA dimensionality reduction is just like a projection. You see a projection here, right? So the PCA dimensionality reduction is just like a projection. So you are trying to find a shadow of the data that is still informative about what the original data is. Okay. So you can see the same thing here. So we plot the variance, create a scatter plot, and get the average log samples. Okay, so you can see you actually get a transformation. Now this tells us that how many dimensions are in our data. It's basically a rough indication. It's called scree plot, and it tells us the amount of variance that can be attributed to each of the factors. And what you see is, even though we have 64 variables, this goes up to 64. We only need one or two to account for a larger chunk of variance in our data. Okay, so that's good. That means that dimensionality reduction could be very successful. So what I'm going to do then is I'm going to actually plot the projected data onto the first two principal components. Okay, so I'm now going to plot the projected data into the first two principal components. So we are going to do just a two-dimensional analysis. Okay, so I have to write the code for that. So SNS dot scatter plot x equals to train.tf will go up to 0, y equals to trend tf will go up to 1, that style equals to y training, 2 equals to y training, and palette equals to red, green, blue. Okay, fine. Let's plot this. Again, what happened? Style equals to white training line 24, invalid syntax. Acha. Again, X training TF 0 up to 0 we trained. Y equals to training TF up to 1. Style equals to Y training. Okay, fine. U equals to Y training. And palette to red, green, blue. Okay, this should work. So what we did was we knew that dimensionality reduction would be very successful. So we projected the data onto the first two principal components. So we are going to do just a two-dimensionality analysis. So we are going from 64 to two dimensions. So you can see there are 64 dimensions, but we are going from 64 to two dimensions, and we will color the points by the class. Okay, so that is what number they actually represent. And what you see here is that in these two dimensions, it's really easy to separate the three numbers. Okay, so you will see there are numbers in red, green, and blue. Again, it's an error from my side, but if you are getting red, green, and blue numbers, do let me know once in the chat. If you're getting red, green, blue numbers, do let me know once in the chat. Okay, so you will see the ones which are in the red. So there are three. There are red, green, and blue. So the ones are up in the red. Okay, the ones will be represented by the red. 3 will be represented by green, and 6 will be represented by blue. Okay, so there might be a bit of overlap, but by and large, there's a lot of separation. Even though we went from 64 dimensions or individual variables down to two principal components. Okay, so there's a lot of separation. So we can also get the log likelihood, which lets us know how well our PCA model reflects the original data set. So, and we have to just keep that number in mind because we are going to compare it with what we get from the testing data. Okay, so now we are going to test the model, and what we are going to do is we are going to transform the test data and get a scatter plot that uses the PCA we just calculated, the model, but it applies to the testing data. So just a second. What we will do is I will just print the log likelihood. So print percentage 2f PCA dot score extern. Okay, fine. So what we will do is, so as I told, the ones you see are in red, the threes are in green, and the six are in blue. So there was little bit of overlap, but there's a lot of separation, even if you are reducing the 64 dimensions to 2 dimensions. Okay, so we got a log likelihood, which lets us know how well our PCA model reflects the original data set. And we have to keep that number in mind because we are going to compare it with what we get from the testing data. So now we are going to test the model, and what we are going to do is we are going to transform the test data and get a scatter plot that uses the PCA we just calculated. So the PCA we calculated from the model, but it applies to the testing data. And what you see here is a very similar model. Okay, so I will just make training data TST TF equals to PCA dot transform PST. So what I will do is I will make a scatter plot along the first two principal directions. So SNS dot scatter plot x equals to TST TF 0. After that y equals to TST TF 1. After that I will style it with YTST, and then we have Q equals to YTST. Again, the palette will be red, green, blue. Again, what happened? SNS dot scatter plot. Did we miss a module here? Acha, we missed the SNS module here. No, we have the SNS module, right? So what did we miss here? What did we miss here? Just give me a second. So just a second. Just a second. I guess we did something wrong up here. Okay, so what we wanted to do here is, so you are going to test the model, and so I wanted to show you a model which was very similar, but it's not working. Let me just check once more. So test.tf equals pca.transform x test. Acha. Shit. So much of typo. Again, I will get a typo here. These little things Okay, so I guess this will work. Okay, so now you will see this is a very similar model. Okay, so you saw this model here, and this is a very similar model to the previous one. So the model has transformed well from the training data to the testing data, and we still have very clear separation here. So between the three different classes, the three different digits that are the outcome variable, even when we reduce from 64 variables down to the two components. And if you want to compare the average log likelihood up here, we had so we had here up 189.72. Okay, we had here 189.72. So once more I'm going to print it for the testing data set. So just okay, fine. So print dot 2f PCA dot score it's PST. Let's see what we get here. Oh, we still have it 189.72. Okay. So basically, the important thing is that those numbers are very close and it's almost similar. So we are not getting any difference here. We're not getting any difference here. So that's something new to me. So the numbers are exactly same, and it's let you know that the principal component analysis has transferred well from the training data to the testing data and gives us a lot more confidence in our results as something that we can use to then move ahead in our analysis with clear, more consistent data set. So let me know, did you get the same numbers for the training and the testing data? Let me know once in the chat. Acha, need break. Acha. Dhananjay, is it okay to get a break? Acha. You got 185.23 in the test. Acha. And what about the training? Dayal, what about the training? Puneet, yes. You need the OPT digits dot training and dot test. Okay, you don't need the OPT digits raw right now. We dealt with that sheet at the first step. Okay, so this is the second step where we are deep diving into PCA. So for PCA, you need OPT digits underscore TRN and OPT digits underscore TST. Okay. 179.45, 180.2. Okay, very close. So 189.72. Okay, fine, great. In training, 189.72 in training, and how much in testing? Rutvik, how much in testing? 185.23. Okay, that's again very close. That's again very close. So it's the important thing is those numbers are very close to one another, and it lets you know that the principal component analysis has transferred well from the training to the testing data. Okay, so you should be confident now in your results, and we can move ahead with our analysis with a clearer and more consistent data set. So that's important. Abhishek, I think it will be available. I think. Yes. I will share the codes. I will share each and every file of the exercise to all of you. Okay. No worries on that part. 186.52 in testing, and how much in training, Tony? How much in training? Okay, so just a second. Just give me a second. Just give me a moment. Okay, so now we will be looking at the next approach, which is linear discriminant analysis. So for the linear discriminant analysis, I will just share the files which are needed for that. Just a second. Just a second. I will share each and every file. So no worries on that part. Okay. I will share each and every file. So now you have the training and the testing data, right? So we don't have to import any more thing. So what we will do is I'll just import one more library here. I will just import one more library here. So I need to import the LDA. So for that, I will write from sklearn dot discriminant analysis import linear discriminant. You can write anything. You can write LDA as well. So let's just write the full form. Discriminant analysis. Okay. Let's run this. 187 and 182 very close. Very close. Sunil, we are about to end in few more minutes. Like I will be ending by 8:15 because I have to go and catch a flight. But I will end at 8:15, and we will have a question answer session then. Okay, we will have a question answer session then, and we will end up at 8:30. So I will just show you the LDA part once. Then we will go to the we will jump into the question answer session. Okay. So, okay, I will have to run all the files. So, LDA is another interesting approach, so it's called dimensionality. So like it's an interesting approach to dimensionality reduction, and it's called linear discriminant analysis. So what's unusual about this is it's not actually a dimensionality reduction algorithm. It's not actually a dimensionality reduction algorithm, but it's a classification algorithm that uses dimensionality reduction to do its classification tasks. So it's not a dimensionality reduction algorithm, but it uses dimensionality reduction to do its own classification tasks. So I want to show you how this works, and you will see that to a certain extent. So let me just run all these once. So you need to have this library from sklearn.discriminant analysis import. You can name this anything. I wrote the full name. You can name this anything. So you have to import this library. Okay. Otherwise, the code will not work. Let me just. Okay. No, Setu. There's no impact on that. The questions are, just to make sure that you guys are actually going through the session. You guys are actually learning something through the session. Okay. And I won't say this is a beginner friendly session, obviously, because at the starting of the session, I told you must be familiar with Python programming language. You must be familiar with some data exploration stuffs, with some statistical concepts. So I told that before, right? So for somebody, it might go above the head, but obviously data mining is not an easy task. Thing is, I'm not getting what is happening. Acha. LDA isn't working. LDA isn't working. This line not working. From sklearn discriminant analysis import linear discriminant analysis. This line not working. Just let me know once. This line not working. Just let me know once. Okay, so now we are ready to move into LDA. So first what we will do is we will load and prepare the data. So we have already the training data set and the testing data set, right? So we will load that. So again, I have to write trn equals to td dot read CSV sample data opt digits dot CSV. Okay. After that, x training equals to training dot filter regression expression. Y training equals to training dot y. I'm actually happy to see that there are still 350 plus students in the chat. So that's quite motivating actually. That you guys are actually uh, you actually care about learning new things. So that's really motivating and inspiring me as well. So that's great. Okay, what happened? We'll read the test data pd dot read CSV sample data opt digits dot test dot CSV x tst equals to tst dot filter regex equals b. Okay, now y tst equals to tst dot y. Okay, let's run this. So first we have to load and prepare the data. So the loading and preparing part is done. So you will see to a certain extent that it looks a lot like principal component analysis. So it looks a lot like PCA, but it gives some different output. So we have already loaded the package. So okay, what we are doing here is okay. So we have imported the data set and we have splitted it into testing and training with X for the attribute or pixel data variables and Y for the class variable that says whether a digit is a 1, a 6 or 9. Okay. Now we will take a look at the first few rows of the training data. Okay. So for that we have to write train.head. Okay, so now here we have the first 5 rows and the variables P0 to variables P63. Okay, we have P0 to P63, so which are basically numbers of pixels that have been activated within a certain region, and then the Y, like the Y here. So this is like basically the class variable, whether it's a 1 or a 6 or something else. Okay, so now let's do the LDA model. So we will start by training it. So for that, we have to write LDA equals to linear discriminant analysis. After that, LDA dot fit X train and Y train. Okay, so let's train it. Okay, so we have started training it and we set up a LDA object first. Okay, what happened again here? X train, Y train. So we set up the linear discriminant analysis object here, and then what happened here is LDA.fit X train, Y train. Type error if allow none else infinity. Just a second. So what we did here is, I don't know why I'm getting this error. Input contains nan infinity or a value too large for D type. Acha. So what we need to do here is, if we transform this, Acha, let me give you a short brief about what things we are going to do here. So I will share you the exercise file. Okay, I will share you the exercise file. You can just run it afterwards. I don't know what's happening here. Maybe the data set is too large for LDA to work upon this. So that might be an error issue, but you can try it at home. Okay, so what we are going to do here is, so first we will fit the model into the training data, and we will transform the data. Okay, so as we did earlier, we transform the data, we plot the transform data, and then we will get the mean accuracy of classification that is based on this dimensionality reduction approach. Okay, so we will get the mean accuracy of the classification which is based on this dimensionality reduction approach. So once we transform the data and plot it, it will show us that there is a very clean separation for the three groups. Okay, the red, green, and blue groups, which we saw earlier, even with the other approaches. So the 1 digits, the 3 digits, and the 6 digits, you will see it in the form of red, green, and blue. So you will notice a bigger separation in LDA than that we had in PCA. Okay, so in PCA there was a separation, but in LDA the separations will be bigger. Okay, and that's deliberate because the way the dimensions are created in LDA is specifically to get maximum separation between the groups. Okay, so keep that in mind. The way the dimensions are created in LDA, it's specifically to get the maximum separation between the groups, and it will function like as intended, and then you can actually classify the groups. Okay, so we will get the accuracy, and we will have some accuracy around 98 to 99% on the training data. And like with any machine learning algorithm, the real test is always with the testing data. Okay, so we will test the model once again, and after that you can see that the LDA which we got with the training data, when we apply that to the test data, we'll get a plot that matches the one with the training data. Okay, so the one we saw in PCA, there were two plots, right? So both the plots almost were similar, and my plot gave a result of 189.72 for both the training and the testing data. So you will get similar plots even in LDA. Okay, and you will see the separation is very clean. So there will be a little bit of overlap, but the separation will be very clean, and it's actually, you know, a higher accuracy than we like in the testing data. The accuracy will be much higher than that we had in the training data. So if let's say if in the training data we had an accuracy of 98%, okay, we will have an accuracy of at least 99.8% or 99.9%, which is very very crucial. Like even 1% or 2% accuracy in machine learning models is very crucial. So we will get a accuracy of around 98% in the training data set and 99.8 or 99.9 in the testing data set. So this higher accuracy gives us more confidence, and you know, the LD analysis has functioned extraordinarily well. You will get to see that when you perform it with the training and the testing data. So it's something that you could consider when you are up against a new situation. So it's basically like LDA is basically used for classification. So it uses the dimensionality reduction for its classification purpose. Okay, so it's something that you could consider when you are up against a new classification situations where you have a number of dimensions that theoretically could have a redundant information and could be combined through a dimensionality reduction approach. Okay, so that's how LDA uses dimensionality reduction for its classification purpose. Okay, so you can try this code after the session. I will deliver, I will give all the coding files to Dhananjay. He will share it with you guys, and you guys can just go through all the codes. Let me know afterwards if that's working, because I prepared all the codes before this session. I sat in the afternoon, I created all the PPT and all the codes, and then I was going to execute all of those, but it's giving me error. I don't know why. So yeah, that's it for the session. I have to go. I have a flight to catch. But yes, we can hold the question answer session up to 8:30, and then I have to go. I have to beg your pardon. I have to go. So please, if you have any question, please let me know in the comments. Thank you so much. Thank you so much for coming today. Thank you so much, everyone. Thank you so much, everyone. Again, one more thing. I know a lot of people couldn't understand the things, but yeah, data mining is not too tough, but not too easy as well. You have to have, you have to go through it frequently and rigorously to understand the concepts. And there's a lot of thing in data mining. Okay, so it's not an easy task, but once you get the hold of it, you are a god. Fit transform. Okay, let me just check once.
So Sanula, important questions arising. You can look into it, Sanula.
Okay. So basically, data mining, as I told, right? You have to have the data from somewhere, right? So you can have so much of data that you don't even know like where to begin, and you don't know how to, sort through it to get insightful cases. So you can have that much of data and you don't know where to begin with, you don't know how to sort through it to get useful insights, which is the whole point of getting data in the first place. And this is where we turn to data mining. So that's how every sector, like each and every sector, has data miners in them. Like each and every team has it, because data is important. You have to work on the data, but where will you get that data? How will you get the potential data from the tons of data which is available on the internet? So that's how data miners work. Yes, it's like searching and working on the potential data. It's like searching and working on the potential data.
Another question, Sanula.
Okay. I didn't get anything related to data mining in this session. So it's like there's a huge market, and you need data miners. See, it's all about data. Like a company which is getting the data faster than the other company comparatively is much time ahead, much success rate ahead of the other companies. So it's about getting the data, and it's about getting the potential data. So if you have the potential data on which the other team members can work upon, then you can do the same task much faster than the other companies, other like agencies in your sectors. So that's like, it's all about extracting the data. It's all about extracting the data. If you don't have the potential data, on what will the other folks which are associated with you, or like the colleagues which are your colleagues, on what they will work upon, right? So like data engineers. So I'm a data engineer. So data engineers, data scientists all depend on the data. So if you don't have the data, on what will we work? Thank you, Nairit. Thank you, Nairit. Thank you so much. How to give attendance? Okay, someone asked a question. Is it important to learn Python language to do this? You can do it in R as well. And yeah, these are the two most preferable languages, Python and R. Okay. Sunil, the lecture has ended at 8:15 and we are just taking up some few questions. Okay. Okay, I will share the collab link. I will share the collab link. Actually, I will share all the exercise files which I created for you. Okay, so that you can just extract it from the exercise file to Google Colab, and you can run all the individual columns. Okay, so after that, if you have any, if you can't understand the things, you can directly reach out to me. Coding Ninjas will also help you in that case. Okay. How will it be shared to us, Dhananjay? How will you share this? Do you have anything in mind? Like, are the folks going to get any assignment after this?
I think Sanil. So guys, like you will be receiving all the details and all at the end of the bootcamp, 5 days bootcamp. You will receive via email as well as through WhatsApp. So don't worry regarding the same.
And I have few assignment questions for you guys. So I will be sharing that with Dhananjay. So that will help you to know actually if you could understand the things correctly. Somebody is asking about certificate.
Guys, don't worry about the certificate. You will receive all the certificates by the end of the 5 days bootcamp. That is on February 1, maybe most probably 1 or 2. So don't worry. One interesting question coming in, like why we have to mine? That's mainly need for of it. Sunny.
Why do we need data, first of all? Why do we need data, first of all? So if you have answer to that question, you know why we need mining. It's all about, identifying the patterns.
Somebody is asking what is your CTC?
It's not much, and I cannot disclose that so openly. But you can see the amount in some of my videos present on YouTube. It's close around uh, 1.8. It's close around that. Okay, Dhananjay, I think we can wrap up.
I think yes. So, guys, we have reached the end of today's session, and I hope you all have learned a lot from Senul. And I want to thank each and every one of you to act for active participation, enthusiasm, and willingness to learn. That you stay till the end of the bootcamp, and you have shown that you are capable of achieving more than your thought possibly, right? And a special thanks to Sanul who has shared his expertise in data mining, big data. I hope you have enjoyed his life project. And once again, thank you for attending. And I hope to see you all again tomorrow at 6 p.m. with Shambhavi, who will be doing projects related to data analytics and all. So keep in touch, stay curious. Thank you so much. Thank you, Sanil, so much for your time.
Awesome.
And happy
Good night,
journey for
everyone.
your trip to Warsaw. And
Bye bye. Good night,
all
everyone.
right.
Bye.
Bye bye. Thank you.